Section 1 Introduction. We're going to delve into the world of reinforcement learning, RL, specifically offline and online RL. Offline RL is a method that uses previously collected data to train policies, which is particularly useful in areas where data collection is costly, like robotics or healthcare. However, it can be challenging when the data is suboptimal and doesn't cover enough ground. For instance, a dataset on robotic grasping might not be enough to teach a robot how to grasp and then hammer a nail. On the other hand, online RL is more about deciding what kind of data should be collected, or in other words, exploration. It's useful for fine-tuning offline RL policies. For example, exploration bonuses can encourage an agent to visit new states, increasing state coverage. As the state coverage increases, these bonuses decrease until a high-performing policy is achieved. However, in complex real-world environments, we often don't have enough time or resources to explore the state space sufficiently. This can lead to a bias towards exploratory behavior, rather than efficiently completing the task. So, the question is, can we achieve high-performing policies while still benefiting from increased state coverage from exploration bonuses? Previous works have often combined offline and online RL by first training on offline data and then fine-tuning online. But we propose a different approach. We suggest using offline RL to retrain policies collected with highly exploratory online algorithms. This method, which we call offline to offline RL, separates exploration from exploitation. It allows for high optimism for state-covering exploration, which is more likely to find high-reward regions but less likely to yield optimal policies. Then, it uses a conservative approach to recover policies that can maximally exploit the discovered high-reward behaviors. In the OOO framework, we use an optimistic exploration policy to interact with the environment, and then train an exploitation policy on all the data seen so far. This removes any bias introduced by the intrinsic reward bonuses, allowing the exploitation policy to recover a high-performing policy even when the exploration policy is behaving suboptimally for the task reward in favor of further exploration. We've tested the OOO framework on fine-tuning tasks for adroit manipulation and Franca Kitchen from the D4RL benchmark. The results showed an improvement in the average performance of implicit Q learning by 26% and CalQL by 14%. We also improved the performance of RLPD by 165% on sparse locomotion tasks. In terms of related work, there has been significant interest in offline pre-training with online fine-tuning in recent years. Some methods aim to propose RL algorithms that are suitable for both offline and online RL. However, these methods may be too conservative. Other methods have targeted the offline to online fine-tuning setting, often by changing a regularization or pessimism term to be less conservative during the online phase. Balancing exploration and exploitation is a key aspect of RL research. There's a lot of work that uses extrinsic exploration bonuses coupled with reward-based optimization. However, it's often difficult to balance intrinsic and extrinsic rewards in high-dimensional domains in practice. Our OOO approach addresses this challenge by separating the exploration and exploitation agent. Finally, several prior works study self-supervised exploration. These methods decouple out of necessity. Because the task reward is not available during pre-training, these methods first pre-train an exploration policy without task rewards and then train an exploitation policy when the reward becomes available. We find that separating exploration and exploitation is still helpful even when the task reward is available throughout pre-training and fine-tuning. Section Summary. Offline reinforcement learning, RL, is useful for pre-training policies from existing data, but online RL is needed for exploration. However, online RL alone may not provide enough coverage. To address this, we propose the offline to offline RL framework, which combines offline and online RL. OOO uses an exploration policy to interact with the environment and an exploitation policy for evaluation, allowing for better state coverage and improved performance. Section 3 Problem Setup. We're setting up our problem as a Markov decision process, or MDP. This is a mathematical model used for decision making, where outcomes are partly random and partly under the control of a decision maker. In our MDP, we have several components. 1. The state space, which represents all possible states our system can be in. 2. The action space, which represents all possible actions that can be taken. 3. The transition dynamics, which describe how our system moves from one state to another based on the actions taken. 4. The reward function, which gives us a numerical value for each state action pair, indicating how beneficial it is. 5. The discount factor, which is a number between 0 and 1 that determines the importance of future rewards. 6. The initial state distribution, which describes the probability of starting in each state. We also define a policy, which is a strategy that the decision maker can follow. The value of a policy is calculated as the expected sum of discounted rewards, starting from a given state and following the policy thereafter. The best policy is the one that gives us the highest value. We also define a state action value function, which is the expected sum of discounted rewards, starting from a given state, taking a specific action, and following the policy thereafter. Our goal is to maximize the value of the policy after a certain number of interactions with the system, using a dataset of previous interactions. In the next section, we introduce a framework for learning two separate policies, one for exploration, interacting with the system to gather data, and one for exploitation, making the best decision based on the data gathered. This separation allows us to explore the system optimistically, while removing any bias from the rewards in the exploitation policy. We then discuss how this framework can be used to balance the data distribution for better exploitation policies, especially for difficult exploration problems. We also discuss how to implement this framework using specific reinforcement learning algorithms and exploration bonuses. Our framework consists of two policies, an exploration policy for interacting with the system, and an exploitation policy for making decisions after training. The exploration policy is pre-trained on a dataset of previous interactions, and then fine-tuned through interaction with the system. The exploitation policy is trained on all interaction data after the exploration phase is complete. In general, the same parameters are used for both policies, but in our framework, we separate them. This allows the exploitation policy to be trained exclusively on the task rewards, removing any bias introduced by the exploration rewards. This approach requires more computation, but it doesn't require any additional interaction with the system, which can be beneficial for practical decision-making problems where data collection is expensive. Section Summary. We formulate the problem as a Markov decision process, MDP, and aim to maximize the value function by learning a decoupled set of policies for exploration and exploitation. The OOO framework consists of an exploration policy pre-trained on offline data, followed by online interaction and an offline retraining step to train an exploitation policy. This decoupled training allows us to remove bias introduced by exploration rewards and improve policy performance. Section 4.2 Reweighting data for exploitation. In this section, we'll discuss how we can adjust the data we use for training to improve the effectiveness of our exploitation policy, particularly in situations where rewards are sparse and hard to come by. When we're gathering data online, it can often be heavily skewed because sparse rewards are rarely collected. This imbalance can make it difficult to extract a useful policy offline, which can negatively impact the quality of our exploitation policy. Our approach allows us to adjust the balance of the data we use when learning the exploitation policy, without affecting the data or policy learning for online exploration. To explain this in simpler terms, let's say we have a set of all transition data from the environment, and another set of transitions that achieve the sparse reward. To increase the likelihood of training on high reward transitions, we can upsample transitions from the set of high reward transitions. This is done by sampling transitions from both sets, with a certain probability for each. This same approach can be applied to situations with dense rewards as well. Next, we'll provide an example using independent Q learning, IQL, and random network distillation, RND. Our framework doesn't make many assumptions about how to implement the value function or the update functions. We'll use IQL as the base reinforcement learning algorithm for both update functions, and RND as the exploration bonus used in the optimistic update. IQL is particularly useful because it avoids pessimistic Q value estimates for states not in the offline data, making it more suitable for online fine-tuning. RND is effective in large and continuous state spaces, where count-based bonuses can be difficult to extend. For the exploitation policy, we can define a set of variables including the policy, Q value, estimated Q value, and value function. For the exploration policy, we add a few more variables including the exploration bonus. The pessimistic update follows the update equations for IQL. For the exploration policy, the optimistic update follows the same equation, but we add the intrinsic reward to the task reward. This means we optimize a function that includes both the task reward and the exploration bonus, with a parameter that controls the trade-off between the two. Along with the policy parameters, the R&D predictor network is updated to regress to the target network in the optimistic update. In our experiments, we study the effectiveness of separating exploration and exploitation on a range of tasks with different levels of exploration. We use a simple example to illustrate the need for aggressive exploration and a separate exploitation policy to achieve a high-performing policy. We also test our framework with several recent offline to online RL algorithms, and evaluate it on several environments with a focus on hard exploration. We conduct several studies to isolate the effect of separate training, analyze the performance of our framework in the context of the primacy bias effect, and understand the role of offline retraining for exploitation policies. To illustrate the exploration bias, we consider a somewhat exaggerated example. In this experiment, we have an environment where the goal is to reach a certain location, marked by a red apple, to receive a reward of +1. There's a wall in the environment, and the agent has to find a path to the goal that avoids the wall. The offline data in the environment shows a suboptimal path that goes over the wall, but the optimal path goes under the wall. How do we learn the optimal policy that goes under the wall? When we use IQL for pre-training and fine-tuning, the policy only explores around the suboptimal data in the offline dataset, and thus, recovers the suboptimal policy in the process. To learn a policy that takes the shorter path under the wall, the agent first needs to substantially increase state coverage. To that extent, exploration bonuses can be effective. For this experiment, we consider a simple count-based bonus. As shown in our results, with a coefficient of 5.0, the state coverage can drastically improve, and includes visitations to the goal through the optimal path. However, the policy performs worse than the IQL. Since several parts of the environment have not been explored and the weight on the intrinsic reward is large, the agent is incentivized to keep exploring the rest of the state space. In our decoupled framework, offline retraining allows the exploitation policy to maximize just the extrinsic reward, i.e., the sparse goal-reaching reward, without any bias from intrinsic rewards. Trained pessimistically, the exploitation policy can indeed recover the optimal path. Overall, this example shows that offline retraining can recover a high-performing policy long before the exploration bonus decays to 0 when using our framework. Section Summary. In the OOO framework, we can rebalance imbalanced datasets by upsampling transitions achieving the sparse reward, allowing us to train on high-reward transitions and improve the quality of the exploitation policy. An example instantiation of the OOO framework using IQL as the base RL algorithm and R&D as the exploration bonus shows that decoupling exploration and exploitation can effectively recover an optimal policy even in cases where the offline data provides suboptimal paths. Section 5.2 Offline to Online Fine-Tuning and Online RL Evaluation. In this section, we'll discuss the process of fine-tuning offline to online reinforcement learning, RL, and evaluate its performance. We'll start by examining 6 standard environments for this process. 3 of these are adroit environments, where the goal is to perform tasks using a complex, dexterous hand. The other 3 are Franca kitchen environments from the D4RL benchmark, which involve completing a series of tasks in a simulated kitchen filled with common household items. We'll use 2 recent offline to online RL methods, IQL and CalQL, to implement our offline to online OO process. We'll also use R&D as the exploration bonus for all environments. We'll compare our method with 2 others, TD3 plus R&D, where offline data is loaded into the replay buffer for TD3 and an R&D reward is added to the reward function to help with exploration, and PEX, which maintains 2 copies of the policy, one from offline pre-training and one fine-tuned online, and then adaptively combines them online. Our evaluation results show that the performance of OO depends on the base RL algorithm. For IQL, OO can improve average performance by 26.4% for the same fine-tuning budget. Notably, we see improvements of over 165% on relocate binary V0 and over 45% on kitchen complete VO. For CalQL, we first improved the official public implementation by applying the same Monte Carlo lower bound for Q values of uniformly sampled actions, not just the actions sampled from the policy. With this improvement, CalQL can nearly max out the benchmark in the budget used by other methods, i.e., 1 million steps for Adroit and 4 million steps for Franca Kitchen. With a reduced budget of 250,000 steps for fine-tuning on all environments, OO can improve the average CalQL performance by 14.3%. These results suggest that OO can further enhance the performance of state-of-the-art methods by effectively using exploration bonuses. OO, CalQL, provides the best reported results to our knowledge, achieving almost a 99% average success rate on Franca Kitchen environments. We also evaluated the effectiveness of exploration bonuses in environments requiring extended exploration. We considered two environments from D4RL, Ant Maze Goal Missing Large V2 and Maze 2D Missing Data Large V1. We also considered Hammer Truncated Expert V1, which involves controlling a complex hand to pick up a hammer and hit a nail. The expert demonstrations are truncated to 20 time steps, so they only show how to grasp the hammer, not how to hit the nail. Finally, we considered standard locomotion environments from OpenAI Gym, specifically Sparse Reward Ant Sparse V2 and Half Cheetah Sparse V2. For these environments, we found that OO instantiated with IQL significantly outperforms other methods. Particularly, OO, IQL, can learn a goal-reaching policy with a non-trivial success rate on Ant Maze Goal Missing Large V2 when IQL completely fails to do so. For performance on locomotion environment, OO not only improves the performance of RLPD, which fails to see successes, but it improves over the performance of RLPD plus RND by 165%. Interestingly, OO, RLPD, is able to recover a performant policy for some seeds where the exploration policy for RLPD plus RND fails to reach the goal at all. This suggests that OO can improve the learning stability. Overall, the large improvements in these environments suggest that offline retraining can be even more effective when substantial exploration is required. Section Summary. The authors evaluate the offline to online OO fine-tuning method using 6 standard environments and 2 recent offline to online RL methods, IQL and CalQL. They find that OO can significantly improve the average performance of IQL by 26.4% and CalQL by 14.3% compared to their base algorithms. Additionally, OO outperforms other methods in environments requiring extended exploration, achieving non-trivial success rates and improving learning stability. Section 5.3 Empirical Analysis. In Section 5.3, we delve into an empirical analysis. We observe that intrinsic rewards, which are internal motivations for the agent, do not disappear during the training process. This is evident from the average intrinsic reward the agent receives over the last 1,000 steps on 2 environments, Ant Maze Goal Missing Large V2 and Relocate Binary VO. Interestingly, the intrinsic rewards do not reduce to 0 in either case. In fact, for the Ant Maze Goal Missing Large V2 environment, these rewards increase over time. This suggests that agents who continue to optimize for intrinsic rewards will keep balancing between exploration and exploitation, even when there's ample high-quality data available for training a robust policy. We then try to understand why OORL, out-of-order reinforcement learning, performs better. There are a couple of theories we consider. The first hypothesis is that the improved performance is due to increased state coverage, which leads to a better policy and sufficiently counteracts the bias from non-zero intrinsic rewards. We compare the performance of IQL, incremental Q learning, IQL plus RND, random network distillation, and OO, IQL, in a few cases. We find that while RND can enhance performance in several instances, OO can improve performance even when IQL plus RND does not, or even negatively impacts performance. This suggests that while increased state coverage can be used to learn a good exploitation policy, the policy learned doesn't necessarily utilize this increased state coverage. The second hypothesis is that the improved performance is due to mitigating primacy bias. Primacy bias refers to the tendency of Q-value networks to overfit to initial data, leading to suboptimal policies. Some recent studies suggest that reinitializing Q-value networks during training can help reduce this bias. However, Our comparison between OO and training an exploitation policy from scratch while still using the intrinsic rewards the exploration agent uses, OO plus frozen R&D, at that time step shows that mitigating primacy bias does not sufficiently explain the improvement in performance. In fact, OO plus frozen R&D performs significantly worse than OO. This suggests that the improved performance under OO is due to mitigating the exploration bias by removing the intrinsic reward when training the exploitation policy. We then ask whether exploitation policies need to be trained with a pessimistic algorithm. Some suggest that with enough exploration and state coverage, standard RL can recover performant policies without pessimism. To test this, we train the exploitation policy using TD3 instead of IQL. However, we find that standard RL fails to recover a performant exploitation policy, as the Q values explode when using TD3. While R&D does increase state coverage, for large environments like those evaluated in our experiments, pessimism in offline retraining is a critical component for learning a performant policy.